Hello everybody, my name is Tanmay Singal and today I would like to talk to you about a work which I have been doing with my collaborator Min-Hsiu Hsieh. The title of this work is Random Transvections Approximate Unitary 2 and 3 Designs. Now we all know that the Haar measure plays a significant role for various applications in quantum information and computation. For instance, the decoupling protocol, which is used for various quantum capacity theorems, or the verification of quantum devices, which is used, for instance, in randomized benchmarking. Also, it is useful to study more generic problems in physics, for instance, the thermalization of isolated quantum many-body systems, the black hole information paradox, quantum chaos, etc. Now, to implement a Haar random unitary is inefficient, which is why we are interested in the implementation of what are known as unitary T designs. A T design is a finite ensemble of unitaries which share up to Tth order moments with the Haar measure. Okay. Now, to implement a T design exactly, one needs to implement the quantum circuit for each unitary. If the number of qubits is n, then let's look at the scaling. For a 2 design, the number of elements is 2 power 4n, whereas for for the Clifford group, which is a 3 design, the approximate number of elements is 2 power 2n squared. Now let's compare this with the estimated number of protons in the universe, which we will assume is our limitation. Okay, that is 2 power 266. This limitation tells us that we can implement a 2 design up to only 67 qubits. This is perhaps okay for near-term quantum computers. But for the Clifford group, the limit is 11 qubits. So we see that this is severely constraining. Of course, there are more realistic constraints and which would limit n even more. Due to this, we are interested in an alternative to exact designs, which introduces the notion of asymptotic designs. Now, what is an asymptotic design? Well, consider an ensemble epsilon. So the ensemble comprises of unitaries where the ith unitary occurs with a probability pi. Okay. Now this epsilon is an asymptotic T design when its k-time implementation becomes a unitary T design in the k tends to infinity limit. Okay, when your ensemble epsilon is an asymptotic T design, then you are interested in its convergence rate. Okay, so what is the convergence rate? Well, you want to study this k as a function of n and some distance, such that the k-time implementation is that distance close to the exact unitary T design. The metric that is used is that of the diamond norm. Okay. Now, in our work over here, we introduce an asymptotic 3 design. This epsilon, that is our ensemble, which is an asymptotic 3 design, it comprises of transvection Cliffords, which I will briefly introduce in this slide. Consider an E to be a Hermitian n-qubit Pauli. Okay. Using E, define a linear operator of this form. Okay. This is a unitary. Okay. What's more, it's actually a Clifford, and these type of unitaries are known as transvection Cliffords. Okay. Now there are as many transvection Cliffords as there are Paulis, which you can easily see due to this. These transvection Cliffords, they have some pretty important properties which we use in the proof of our scheme and our result. Okay. So now let's come to the scheme and the results. The scheme tells us that we need to implement a random Pauli once, and then implement the following k times, a random transvection. So after you implement a random Pauli once, implement a random transvection and do this k times. Okay. This scheme is an asymptotic design, meaning that in the k tends to infinity limit, we get a 2 and 3 design exactly. Okay. The convergence rate is given over here on the right. We see that you have to implement the scheme, the number of times that you have to implement the scheme for a unitary unitary 2 design for epsilon closeness is just log of 1 by epsilon. Okay. Whereas for a 3 design, you have to first implement this scheme n times, where I would like to remind you that n is the number of qubits, and then you start hitting close to the epsilon closeness. Okay. As a byproduct of the methods which we employed for our scheme, We also obtained the partial decomposition of the three-copy adjoint representation of the Clifford group. We note the appearance of some of the irreps which were found in Helson et al. In this work, Helson and his collaborators gave the full decomposition of the two-copy adjoint representation of the Clifford group. And some of their irreps, unsurprisingly, also are found over here, but we found the specifics of how many times they occur and what the subspaces look like, etc. And in addition to that, we see, as expected, some new invariant subspaces which have not been seen before. Okay. Future work will revolve around this decomposition, proving that these invariant subspaces are irreps or whether they are further decomposable or not, and such related issues. Okay. So with this, I close and I would like to thank you for your attention.